Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're looking at how you solve second-order homogeneous differential equations with constant coefficients. Now, what exactly are those? Well, they're nowhere near as bad as they sound. Second order means that you have d2y by dx squared in the equation. Constant coefficients means that a, b, and c here, they're just all normal numbers, they're constants. So we're looking at how you solve a differential equation that has this form. What we do is we use the substitution y equals ae to the power of nx. Now to substitute that in, we need to find dy by dx and d2y by dx squared. dy by dx will equal na e to the power of nx. d2y by dx squared will equal n squared ae to the nx. Now substituting those three things in will give us an squared a e to the nx plus bn a e to the nx plus c a e to the nx equals 0. Factorizing that gives us a to the nx times by this quadratic, an squared plus bn plus c equals 0. Now for this to equal 0, one of these two things has to equal 0, but exponential functions never equal 0. So that means that an squared plus bn plus c must equal 0. This equation has a special name. It's called the auxiliary equation. Often that's just abbreviated to AE. And you'll notice you don't have to do all of this working to get there. If you look at the original differential equation, the d2y by dx squared becomes n squared, the dy by dx becomes n, and the y doesn't become anything at all. So you just get an squared plus bn plus c equals 0. And you can always go straight from the question to the auxiliary equation. We solve this quadratic, and as with all quadratics, there are three possibilities. And those three possibilities do lead to three very different types of solution. Type 1 solution is where, when you look at the discriminant, is positive, strictly positive. It's greater than 0. So the auxiliary equation has two distinct real roots, and we'll call those n1 and n2. If that's the case, then the general solution of the differential equation can be written down straight away. And it'll be y equals ae to the n1x, that's the first root, plus be to the n2x, the second root. So these questions are quite quick. You can go very, very fast from the question to the general solution. And it's possible to prove that this is a solution of the differential equation by substituting y dy by dx and d2y by dx squared into the original equation. And we'll do that actually when we do the first example. So that's type 1, as we've just said, and we'll go straight to the first example, which is find the general solution of 2 d2y dx squared minus dy by dx minus 3y equals 0. And as I said, we'll then verify that this answer really does satisfy the differential equation by substituting it in. Okay, there's a summary of what you need to know. I'll let you have a go at working your way through this example by yourself, first of all. So have a go at doing that, pause the video, and then come back to me again when you're ready. Okay, let's have a look at this. Now, as I said, you can always go straight from the question to the auxiliary equation. So if that's the question, then the auxiliary equation will be 2n squared minus n minus 3 equals 0. When we factorize that quadratic, we get 2n minus 3 times n plus 1. So we have two distinct real roots. The first root is minus 1, and the second root is 3 over 2. And we do just substitute those two values in there, and we get to the answer straight away. So the general solution is y equals ae to the minus x, when we substitute in the minus 1, plus be to the 3 over 2x, when we substitute in the 3 over 2. Now that's the question done, but we have been asked to verify that this really does work as a solution. Now, in order to verify that, we need to substitute in y dy by dx and d2y by dx squared. Well, dy by dx, when we differentiate that, will give us this. d2y by dx squared, when we differentiate a second time, will give us that. If we then substitute all of those three things into the equation, then we get this, multiplying out the brackets, gives us that, and then various things can be collected together. And when you collect them all together, you get nothing on the left-hand side. You've got 2ae to the minus x, plus another 1 here, take away 3 there, that cancels those out. And the plus 9 over 2be to the 3 over 2x cancels out with the minus 3 and the minus 3 over 2 here. 0 equals 0. We've proved that this solution does actually work in the differential equation. Okay, a type 2 solution. So coming back to the auxiliary equation and the three different things that can happen when you solve that equation. The second thing that can happen is that b squared minus 4ac, the discriminant of this equation, is equal to 0. Now, if that's the case, the auxiliary equation has got two real repeated roots. So you'll get the same root twice, which is why we've called both of them n1. And if that's the case, then the general solution is y equals a plus bx times by e to the n1x. And you'll notice an x creeps in here, which wasn't in the first solution. That often happens when you're solving differential equations and you have a little bit of an issue. Just throwing in an x, surprisingly frequently, solves the problem. Okay, I'll let you have a go at doing one of this type of solution. So we've got the differential equation, d2y by dx squared plus 6dy dx plus 9y equals 0. Have a go at solving that, pause the video, and come back to me when you're ready. Okay, let's have a look at this. So the auxiliary equation we can write down straight away. That's n squared plus 6n plus 9 equals 0. And that does factorize into two identical brackets, n plus 3 times by n plus 3. So we've got repeated roots, both of which are equal to minus 3. All we have to do is substitute that value into here, and we'll get the general solution. A plus bx times by e to the minus 3x, because that's the repeated root. Now, as always with quadratic equations, the most difficult and confusing of the possibilities is if the discriminant is negative. Now, if the discriminant is negative, then the auxiliary equation will have two complex roots, n1 plus or minus I times n2. The general solution is given by y equals e to the power of the real part, n1 times by x. And then in brackets, we've got a cos and the imaginary part times by x plus b sine times by the imaginary part times by x. Okay, I'll let you have a go at doing a type 3 question. The differential equation is d2y by dx squared minus 2dy dx plus 3y equals 0. Have a go at solving this, pause the video, and come back to me when you're ready. Okay, let's have a look. So this time the auxiliary equation is n squared minus 2n plus 3 equals 0. The discriminant is negative. Solving it using the quadratic formula would give us that. And that all tidies up ultimately to n equals 1 plus or minus 2 times by I. Now the general solution will be y equals e to the real part times by x. The real part is the 1. A times by the cosine of the imaginary part times x, which is the root 2, plus b sine the imaginary part times by x. But as complicated as these questions look, they're surprisingly fast. And once you've done one of them, the truth is you can do all of them. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 109 and have a go at exercise 6A. Thank you very much for listening, and cheerio.